Okay, I want to reshare the screen now. Okay. So we're still on same thermomechanical pulping. So
Yeah, sorry, ma.
yeah,
But please, can you let Busayo in? A classmate of ours said that you
Victor,
that
thank you so much. I'm in already.
she's
okay.
in. Yes.
Yeah, thank you,
Okay,
ma'am.
it's okay. So we're still looking at TMP. So TMP consume a great deal of electrical energy. So much effort has been spent over the years to reduce this. A major early approach was the use of higher temperatures to soften the lignin. This occurs in RMP by steam generation in the process. So instead of going ahead to continue using electricity, steam is generated in the process and put back to help soften the lignin. So in TMP, pressurized steam is applied before and during refining to raise the wood temperature to soften the lignin. TMP process reached commercialization in the 1970s. The process evolved slightly over the years to a typical one shown below. Chips are preheated and refined in pressurized refiner called primary stage. The pulp from this stage is moved to the second stage. I think you saw what I showed before. So in the early days, second stage was an open discharge refiner. In more modern systems, both stages are pressurized. So something like this. So the chips are fed in there, preheated, and then passed in through the screw feeder inside the primary refiner, and then it moves into the tank feeder, goes into the secondary refiner, moves on the pressurized cycle. The heat is recovered and put back and used. So instead of continuous application of electricity, because it consumes a lot of electricity, so heat is generated and steam is generated and used back. It should be noted that TMP did not lead to the anticipated reduction in energy consumption. It did not do so because upon lignin softening, fibers break out of the wood matrix through the middle lamella rather than the primary layer, leaving the lignin-rich fibers surfaces. This gives stiff, poorly bonding fibers. So to make suitable paper-making fibers, much of this lignin must be removed in the fiber development state. This requires increased energy consumption. Other comparisons of the TMP, HGW, you know HGW, what it is, the groundwood, and then RMP. So the TMP requires higher energy, but gives longer fibers, fewer shafts, and less fines, as I've said before. As a result, produces stronger paper and the extent that in many cases newsprint can be made from 100% TMP without any chemical reinforcement of the pulp. So comparing TMP, HGW, and RMP, the groundwood, refiner pulping, and thermomechanical pulping, we have these three methods here. Look at the energy requirements, the freeness, and the rest of the properties. Energy requirements for groundwood method is lower. That of the RMP is lower. The one of TMP is higher, 7.0. Freeness for groundwood pulping method, 100. That of RMP, 130. That of TMP, 100 to 150. I hope you remember that the freeness is, I wish I can ask you a question here. So which one is better? Is it a low freeness or a higher freeness? Is it a low freeness or higher freeness? That is left to you. Go and check your notes again. There's burst index, there's tear index, breaking length, sheave content, long fiber content, fines content, brightness for unbleached pulp before we bleach. So these are the different properties for the different mechanical pulping methods. So a typical TMP process also contains a latency removal step. Latency removal step. This refers to a high core developed in fibers during refining, which is frozen in upon cooling after refining. The high core, so this effect reduces the length of fibers, diminishing their ability to make strong pulp. And so it is important to remove this latency. So the core is removed in a latency test in which the pulp is heated at low consistency in a stirred tank. So during this process, the fibers strengthen out to a large degree. So that curling is that latency which needs to be removed. And the process is that we have seen now, heating it and at low consistency and stirring. And then that latency is removed. That is by straightening the fibers, getting it straight and not curled. So here you have a typical TMP process. I've shown you different processes. The first one I showed you in the other lecture was an advanced type. And then, I mean, if you can look at all these different steps, you should be able to understand better. I'm showing you different schemes, schematic representation of TMP. So you can look at them very well, and then it gives you better understanding. So screening and cleaning system, which follows all mechanical pulping processes. It's also what is applicable in TMP. And this is important, is an important component of mechanical pulping because the process does not break down all of the wood to individual fibers. So you need to carry out screening, like sieving. It's necessary, therefore, to separate the fibers from the fiber bundles. The fiber bundles are the sheaves. So you separate the fibers from the fiber bundles. That is through screening. So, and here, hydrocyclones are used to accomplish screening. Separated fibers then pass on to a thickener and then to a paper machine. Passes on to a thickener first before it goes to paper machine. The rejects are further refined in a reject refiner and then screened again. So when you do the screening, those are rejects that don't pass through the screen. The one that passes through the screen is what you use. The one that is reject is not passing through the screen, and that is what you now put back to the process of refining, and then you pass it back to screening again. So, and any reject at any time, it has to go back. If you see the schematic presentation I showed you before, 2 slides up, you'll be able to see all that. So, modern chip refiners are a marvel of mechanical engineering. They are a large in size. They operate at high speed. They have a gap less than 1 minute between the rotating, 1 millimeter between the rotating plates. Between the rotating plates, you just have a little gap between the rotating plates. So it's large size of the equipment of the refiner and then operating at very high speed. So a typical production rate is 300 BDT per day of the refiner, of one refiner, 800 of a typical gap between 0.5 to 1 millimeter. Typical specific energy, 7 gigajoules per ton. Typical power to refiner, 20 megawatts. So the BDT here I've explained, bone dry ton. That's what I mean by BDT. Very, very dry. Okay. And we have to refining parameters and their effects on pulp quality. Refining parameters and their effects on pulp quality. There are 2 independent parameters. One, the amount of energy applied to the pulp, and then the intensity of refining. The amount of energy applied to the pulp and the intensity of the refining. These are 2 key parameters that affect pulp quality. So we have the long fibers here, and we have the freeness, decreasing intensity, and specific energy here. So this chart shows you that the amount of energy, the higher the amount of specific energy here, the better the freeness, and then the higher the density, the intensity of refining, the better the pulping. So that is what you see there. Those are the 2 independent parameters that are very key. So we also have refiner speed, increased refining speed increases intensity at the same power. Increased refiner speed increases the intensity at the same power. Lower energy consumption to get the same freeness quality. Lower fiber length, lower tear, higher scattering at the same Canadian freeness, standard freeness. Consistency, increasing the consistency of the pulp in the refining zone. First thing we look at is the refiner speed, that is what it does. And then in consistency, increasing the consistency of the pulp in the refiner form increases moisture content, which increases fiber length, increases wet mass, therefore inertia, which lowers the refining intensity, which lowers fiber length. Increased dilution, lower consistency. Increased dilution is lower consistency, reduces the gap between the plates due to lower stream volume. Decreases power consumption by 7% when 50% consistency gives 30% consistency. So the production rate is another one. Increased production will reduce energy consumption at a constant Canadian standard freeness. It lowers the fiber length and strength. Preheating and temperature is another property we're looking at, another factor we're looking at, preheating and temperature. It's found that preheating is not too important. The temperature.
Sorry, ma.
Yes.
It's past 2. We have another class, ma.
Oh, okay. Sorry. Okay. So we'll continue in our next lecture. We'll continue from here. Sorry about that. So, we'll bring this lecture to an end at this point, and we'll